His explanation was that there's a force, a gravitational force that exists between any two objects in the universe. And so Newtonian gravity explains the orbits of the planets in terms of this force, this gravitational force. The Earth orbits the Sun because there is a gravitational force that's pulling on the Earth, keeping it in its orbit around the Sun. So it explains the orbits, but it also explains Galileo's fact, the fact that falling objects, if they're close together, fall together. And it explains it because Newton's theory of gravity is a quantitative theory. It doesn't just say, oh, there's some force. It tells you how big that force is. And in particular, it tells you that the force, the gravitational force that's pulling the Earth, for example, towards the Sun, is proportional to the mass of the Earth. And if you drop something down to the ground, it's being pulled down towards the center of the Earth by a force that's proportional to the mass of that object. So if I drop a bowling ball, then the force on that bowling ball pulling it down is proportional to the mass of the bowling ball. If I drop the marble, let's say it's 100 times less massive than the bowling ball, then the force on the marble is 100 times less than the force on the bowling ball. The force on the two objects is proportional to their masses. However, Newton's second law of motion says that the acceleration of an object is inversely proportional to the mass of an object. That means that if something is being pulled with the same force, if you have two objects which are being pulled by the same force, and one is twice as massive as the other one, then the object which is twice as massive will accelerate at half the rate. So the acceleration is inversely proportional to the mass. So the force on the larger object is bigger, because on the more massive object is bigger because it's more massive, but its acceleration is inversely proportional to that mass. So the two factors of the mass cancel out, and the acceleration of the two objects is identical to each other. So indeed, Newton's laws of motion and Newton's theory of universal gravitation explains the Galilean fact that falling objects, if you drop them, fall together at exactly the same rate, they accelerate at the same rate, and they will hit the ground at the same time. Newtonian gravity was extremely successful. It was used for decades and centuries to explain and predict the motions of the planets to extraordinary accuracy. However, it had a problem. And that problem goes by the name of action at a distance. So the Newtonian theory of gravity is that any two objects, for example, the Earth and some astronaut, are attracted to each other by this universal force, this force of gravity. And this force can be calculated quantitatively. It depends on the masses of the two objects, but it also depends on the distance between them. The further away those two objects are, the less powerful the force. The force is inversely proportional to the square of the distance between them. So if you double the distance between the two objects, the strength of the force goes down by a factor of 4. If you triple the distance between the two objects, the strength of the force goes down by a factor of 9. So it's inversely proportional to the square of the distance. And this force exerts itself through empty space. There's nothing in between the Earth and the astronaut, which are being attracted to each other. This force is just there. And this feature of Newton's theory was criticized by many thinkers at the time. And one of the thinkers who was around at the time of Newton said the following thing: that gravity should be innate, inherent, and essential to matter, so that one body, such as the Earth, may act upon another, such as the astronaut, at a distance through a vacuum without the mediation of anything else is, to me, so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. So that's a pretty trenchant criticism of Newton's theory of gravity. And the person who made that criticism was Newton. And it's interesting that Newton himself understood, so Newton was a consummate scientist, he understood there was something unexplained about this theory of gravitation, something that was something lacking, something unsatisfactory about this proposal that there should be this force that acts between two bodies and has no carrier, if you like. It acts at a distance between two objects which have nothing in between them. There's just a vacuum in between them. However, because Newtonian gravity was so successful in predicting the orbits of the planets, this more, what one might call philosophical worry, was just set aside, and people just got on with the business of doing science with the Newtonian theory. However, things came to a head in 1905. And they came to a head because Newtonian gravity is in contradiction with the new theory of special relativity that Einstein proposed as the way to understand electromagnetic phenomena. And if you know one thing about special relativity, then you'll know that special relativity tells us that nothing can move faster than light. So there's a universal speed limit in the universe, which is roughly 300,000 meters per second. And that speed limit cannot be 300,000 kilometers per second, sorry. That speed limit cannot be broken by anything, any physical influence. Nothing can signal to any other thing faster than light can propagate from that one thing to the other. However, in Newtonian gravity, the force between two objects changes instantaneously when one of the objects is moved. So think about the Earth and the astronaut. If, for some reason, the Earth moves slightly, suddenly, then instantaneously the distance between the Earth and the astronaut is changed, and the force on the astronaut will be different, and the astronaut will know that. So the astronaut will know that the Earth has moved. That's an instantaneous signal to the astronaut that the Earth has moved. And that's impossible in special relativity. Nothing can travel faster than light. No physical influence can travel faster than light. So this was now a scientific, physical contradiction between two theories, and that constituted a major crisis in physics. So no longer could people just sit around and think, well, there's something odd about Newtonian gravity, but it works so very well that we can just brush it under the carpet. Now there was a genuine crisis, a genuine contradiction between two different physical theories. But this crisis took 10 years to resolve between 1905 and 1915. The resolution was general relativity. So the resolution of this crisis was the creation of the theory of general relativity. And the first step is something that we all have evidence for from our own intimate experience. So we can take the first step that Einstein took in working out general relativity, and we can take it now. We can all have the experience that constitutes taking that first step, and you can have the experience sitting from the comfort of your own chair. Now that's very interesting. According to Newton's theory of gravity, there are two forces on you as you sit in your chair. There is the gravitational force of weight pulling you down, and to counterbalance that, there is indeed a pressure from your chair pushing you up. That's Newton's theory of gravity. That's how Newton's theory of gravity would analyze the forces on you sitting in your chair right now. However, I claim that if you free your mind from analysis and learnt theories, the only force that you can actually feel is the force of pressure pushing you up. And you do not feel any force pulling you down. And indeed, in general, or even though the Newtonian theory says that force is there. And indeed, in general relativity, there is no gravitational force of weight acting down on you. It does not exist. There is no gravitational force of weight pulling you down. There is only a force pushing you up from your chair. It's the force that your chair exerts on you, pushing you up. This realization is what Einstein called the happiest thought of his life, and it was the first step. It was the first step that he took towards general relativity. There's no force between the Earth and an astronaut. There's no force between the sun and the Earth. So that explains, of course, the Galilean fact. When you drop two objects, let them go from rest, those two objects, there's no force on them. There's nothing pulling them down, no force on them at all. They move completely freely in a force-free way. And because they're moving completely freely, of course, they stay together because there's no force on them. They just stay together. They move together because there's no force on them. But how can we understand the motion of the orbits of the planets? So Newton's theory accords with our experience of whirling something around on a string because it says, well, something goes in a circle because there's a force on it, a force towards the center. Einstein's theory says there's no force of gravity. So how do we understand planetary orbits? Newton could not have understood that because Newton did not have what we now have, what physicists in the early 20th century had, due to the work of Faraday and Maxwell, and it's particularly pleasing to mention Maxwell here in this particular place to which he is so closely associated. Faraday and Maxwell had introduced to physics a new notion, the electromagnetic field. The electromagnetic field is a material substance that pervades space and time. It's everywhere, this electromagnetic field. They used it to explain electromagnetic phenomena. Einstein knew that he had to postulate something analogous to that for gravity, a gravitational field that is everywhere. And the extraordinary thing was that this gravitational field is, it turns out, space-time itself. So the electromagnetic field of Faraday and Maxwell lives in space-time. The gravitational field of Einstein is space-time. And it turns out that to explain phenomena such as the orbits, this geometry of space-time has to be curved. Massive objects, such as the sun and the earth, create warpage in space-time itself. And other objects which are moving freely in space-time will move in that curved space-time as if they are being attracted to these massive objects by a force. There is no force there. They are just responding to this curvature of space-time. So the moon is moving freely in a curved space-time around the Earth, and it looks as if it's being attracted by a force, but in fact it's not. It's just responding to the curvature of space-time.